My name is Brendan John, and today I'd like to talk for a bit on star death. I've always been fascinated by astrophysics. It's such a complex and amazing thing, discovering some of the most mind-blowing things that people have ever heard of. And nothing, to me at least, takes the cake like the death of stars. You see, there are so many different things that can happen, from fizzing out over billions of years to a super dense core with the strongest magnetic fields ever observed. So here we go, straight into the heat of it. After all, plasma is very hot. To get a grip on the insane things that happen after death, you need a decent handle on what's happening when a star is alive. Since it's not what I'm going for today, I'll give you the quick rundown. Stars are composed of superheated gases, otherwise known as plasma. Within the core, the temperature is so high that the atoms of molecules are able to overcome the repulsion away from each other when they get a bit too close, and they fuse to combine into a heavier element. Hydrogen to helium, helium to carbon, carbon to neon, neon to oxygen, oxygen to silicon, and finally, silicon to iron. And that's where we come in. You see, iron can be fused, and some stars do reach that temperature, but upon the fusion of iron, energy isn't released, but it's rather absorbed. So by now, the star is absolutely massive, and without the pressure coming from within the core, the star begins to collapse under its own gravity. Most stars, however, do not reach this stage, instead condensing over time as their temperature lowers, forming a relatively cool and dense white dwarf. This is the fate of our Sun, which is actually quite small in the grand scheme of things. Compare it, for instance, to the largest known star of the universe, UY Scuti, which is somewhere from 1,600 to 1,800 times bigger than it. White dwarfs are generally pretty boring compared to the other routes we'll cover, slowly exhausting their fusion stores until they become too cold to fuse. At this point, they're just an enormous ball of different elements floating as a black dwarf. Some stars go out with a bang, opening up doors to whole new possibilities. For those stars, it starts with the collapse mentioned earlier. After the sudden collapse, all the energy it's built up rebounds in a massive explosion of potential energy that briefly outshines the entire galaxy, expelling gases of various elements from hydrogen on the fringe of the star to uranium coming from the fusion of heavy elements in the blast at 30,000 kilometers per second. This is known as a supernova, or at least it's one type of a supernova. There's another where a white dwarf in a binary system sucks in mass from its partner, becomes unstable, and then explodes. After the supernova, the remaining core is crushed under its own gravity. Normally, as in a white dwarf, the electrons repelling away from each other would be enough to stem the force of gravity. This is known as the Chandrasekhar limit. But in the case of a star massive enough to become a neutron star or beyond, it becomes a supercompacted, physics-bending mass in which the electrons physically combine with protons to form a star made almost entirely of free neutrons, which have a weaker repulsion of each other than electrons. The core is most likely the only place in the universe where quarks, the 6 different particles that make up protons, neutrons, and electrons, are able to break free from their pairs of 3. That is the most likely scenario for the core, but there are many theories. At this point, a simple teaspoon of neutron star is 900 times the mass of the Great Pyramid in Egypt. Some stars spin hundreds of times a second, forming while keeping their high angular momentum, emitting electromagnetic radiation and beams from their poles. These are known as pulsars. The radiation is caused by an electrical field in the star generated by its high rotation, which accelerates protons and electrons on the star's surface. Then, there are the even rarer types of neutron stars, magnetars, a neutron star with the strongest magnetic field that we've ever observed. Neutron stars already have a powerful magnetic field, but in a certain range of temperature, the heat and rotational energy of the star convert into more magnetic power, resulting in 10 to the 11th Teslas of magnetic force, quadrillions of times stronger than our own Earth, which ranges from only 25 to 65 microteslas. But then there are the big ones, the ones that overcome neutron degeneracy pressure and compact until it cannot anymore. So dense with such a high gravitational force that not even light can escape it. A black hole. The problem with the black holes and explaining them is their love of taking everything we think we know and ripping it to shreds. For instance, gravitational time dilation. This turns into a paradox. To an outside observer, something falling towards the center, or singularity, takes an infinite amount of time to reach the center, until we simply cannot see it anymore, as all processes on said object slow down. But on the other hand, for the object that, for whatever reason, isn't destroyed by the tidal forces of gravity, time continues normally, eventually reaching the singularity and is subsequently quite dead. You see? Then there's the fact that infinity and zero are problematic numbers for modern physics, but are necessary to describe a black hole precisely, a point of zero volume in which a star's entire mass is concentrated, and space-time curves infinitely. It just doesn't make much sense. We can see the effects of them, however, by watching stars curve around them sharply, almost like an orbit, or even better, by seeing their flashy cousins, quasars. Quasars are supermassive black holes that eject electromagnetic energy at close to the speed of light and are 100 times more luminous than the galaxies that surround them. Often a star with a quasar in it is hard to be seen because of the glare coming from the quasar. The jet of energy is believed to be formed by matter falling into a supermassive black hole at a greater rate than is typical for a black hole. So there you have it. Star death, short and not so sweet. See ya.